My working life's been devoted to number theory. Number theory is my passion. What is number theory? It's about solving equations in full numbers. For example, we take the equation x squared plus 1 equals 7. The solution to that is the square root of 6. That's not a whole number. We're looking to solve equations in whole integers. That is the numbers 1, 2, 3, 4, 5, 6, and so on. So it hasn't always been that people have tried to solve equations in integers. Originally, people were trying to solve them perhaps in rational numbers or in other kinds of numbers. But let me go back to the old history where these problems arose. So we know the Babylonians on their tablets wrote down systems of solutions to equations of the kind I've been describing. They were solving the equation x squared plus y squared equals z squared. This is the famous Pythagorean triple problem. We just see lists of solutions on the tablets. We don't know exactly how they found them, but they were used presumably for some kind of geometric measurement. Then Pythagoras and his followers described the theorem, the geometric theorem that relates sums of squares. So he explained that the square of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides. And from this solution, geometric problem of Pythagoras, we see why the Babylonians were so interested in these equations. But actually finding integer solutions to this equation was only really studied by the Greeks because those were the numbers they had to hand. They had the integers, perhaps the rational numbers, with which to solve these equations, but it's not in some sense natural. And it wasn't for another 1,500 years that people really got excited about solving equations in integers for their own sake. So after the work of the Greeks, in particular of Diophantus, the subject was not as actively pursued as some other branches of mathematics until the early 17th century. In the early 17th century, a French mathematician by the name of Pierre Fermat became fascinated by these kinds of problems. He read about the work of the Greeks in a copy of a book of Diophantus, which had been edited by a Frenchman named Bachet. And in the margins of this book, he would write down his own observations and his own problems and, on occasion, his own solutions. He would also write out to other mathematicians, particularly the British mathematicians at the time, offering them challenges. Could they solve problems that he'd solved? And the kinds of problems were very much of the kind I was describing. Can you find a square and a cube, for example, whose difference is 2 or whose difference is 4? In other words, can you solve the equation y squared plus 2 equals x cubed or y squared plus 4 equals x cubed? And he found some remarkable ways of finding solutions, in particular starting with one solution and using it to generate many, many more, perhaps infinitely more. He would also have ways of showing that some equations like that had no solutions. And this was even more baffling to his contemporaries.
Pierre de Fermat nasce in Francia, a Beaumont-de-Lomagne, nel 1601. Studia legge e diviene magistrato al Parlamento di Tolosa. Il lavoro giudiziario occupa molto del suo tempo, ma riesce a dedicarne una parte alla sua grande passione, la matematica. Grazie allo straordinario contributo che, pur da autodidatta, darà alla matematica moderna, viene spesso ricordato come il principe dei dilettanti. Il suo interesse principale è rivolto alla teoria dei numeri, a cui si avvicina grazie all'opera del matematico greco Diofanto, l'aritmetica. Studiando i problemi proposti nel libro, Fermat affronta ragionamenti e ricerca soluzioni più sottili. Sfortunatamente destina la maggior parte dei suoi appunti al cestino, ma alcuni commenti trovano spazio sul margine delle pagine. Queste rapide annotazioni sarebbero diventate un preziosissimo documento per generazioni di matematici. Grazie ad alcune brillanti intuizioni, il principe dei dilettanti raggiunge una certa notorietà, che viene ampliata da una serie di ardue sfide matematiche lanciate ai suoi colleghi del tempo. Nel 1637, mentre studia il libro secondo dell'aritmetica, annota ai margini di una pagina un'equazione apparentemente molto semplice e tuttavia irrisolvibile. Senza fornire spiegazioni, scrive un commento che sarà accolto come sfida nei secoli futuri. Dispongo di una meravigliosa dimostrazione di questo teorema che non può essere contenuta nel margine troppo stretto della pagina. Con la sua morte, avvenuta nel 1665, le scoperte di Fermat rischiano di andare perdute per sempre. Fortunatamente, le sue annotazioni sono raccolte dal figlio, che decide di pubblicarle in un'edizione speciale dell'aritmetica. In questo modo, l'ultimo teorema di Fermat diviene noto in tutto il mondo e per più di 300 anni irretirà le menti più brillanti del pianeta.
Fermat was a judge in a small town in France called Beaumont-sur-Lomagne, near Toulouse. Mathematics was actually his hobby. He was the great amateur mathematician. But it's phenomenal what he contributed to mathematics, in fact, to physics and science in general. He was responsible for one of the fundamental laws in optics. Together with Pascal, he initiated the study of probability. He was apparently the first to be able to integrate polynomials, and Newton acknowledges his debt to him. He had many interests, but his perhaps overriding passion, and certainly what we remember, what I remember best now, is his contribution to number theory. He really is the founder of modern number theory. In this copy of Diophantus, he made many notes about various problems that arose from the questions that Diophantus asked. Diophantus asked many, many simple algebraic questions and had no uniform methods really for solving them. He just found some trick to get an answer and would be satisfied with that. Fermat was trying to find something more systematic in this problem of solving equations in integers. So Fermat developed some really very ingenious techniques. The most famous perhaps is what's called the principle of infinite descent. So he would say, well, supposing some equation has a solution, then use that solution to derive some smaller solution. And from the smaller one, you derive a still smaller one. Well, you can't go on like this ad infinitum. Integers can't get smaller and smaller forever, so eventually you run out. You can't apply this process. And therefore, he says, there can't have been such a solution in the first place. So with this technique, he could sometimes prove that certain equations had no solutions. The most famous problem he talked about was what became known later as Fermat's last theorem. So this was the equation x to the n plus y to the n equals z to the n. And he wrote in the margin of his copy of Diophantus, it's impossible, on the other hand, to separate a cube into two cubes, a fourth power into two fourth powers, or likewise any power higher than the fourth into two like powers. For this truly I have a wonderful proof, but this margin is too small to contain it. The margins were quite small, and that was not unreasonable, but it would have been nice if he'd just put a little bit in the margin about what he was thinking about. As he didn't, we have to guess what he actually wrote. Even the actual book where he wrote this down has long since disappeared. And the only way we know about this is because his son published a copy of Diophantus after his death, after Fermat's death, which included all Fermat's marginal notes in it. And from that, we've seen how he thought about such problems. But really, we got no real hint about how he could have tackled this problem. And in the years since, mathematicians have gradually come to accept that he probably was mistaken. There were many other claims he made, and the other claims on the whole have been vindicated. There was one he was hesitant about, called the claim about Fermat primes. These are numbers which are prime numbers, that is, they can't be divided by any number except one or themselves. He claimed that you could always get prime numbers by taking a power 2 to a power of 2 and then to another power. So for example, 2 plus 1, or 2 squared plus 1, or 2 to the 2 to the 3 plus 1, or 2 to the 2 to the 4 plus 1, and so on. And he claimed these would always be prime. Well, he didn't quite claim it. He said he would almost convinced himself, but he didn't quite have it. And in fact, it isn't true that if you take 2 to the 2 to the 5th plus 1, it's actually divisible by 641, I believe. So Fermat had a reputation for being very reliable. He made breakthroughs in many areas of number theory. And in fact, number theory, he really changed it, because when he started as a number theorist, the problems were still rather ad hoc, rather each one you used a new idea, a new technique, but the problems weren't well organized or didn't lead to very sophisticated mathematics. In fact, curiously, the problem which perhaps gave him some fame in his early career was finding the second pair of amicable numbers. So amicable numbers, pairs of numbers like 220 and 284. If you add up the divisors of 220, you get 284. You add up the divisors of 284, you get 220. And at the time in Europe, no one knew a second example of a pair of amicable numbers like these. And Fermat found the second pair. But over the course of his lifetime, he found much more profound problems, such as the one I mentioned. And some of the problems he worked on and he suggested are actually still unsolved today. The problem, what's called Fermat's last theorem that I mentioned a minute ago, is actually solved, and that I would like to explain.
Nel 1637 Fermat annota sulla sua copia dell'aritmetica un'osservazione apparentemente semplice, ma destinata a diventare uno dei problemi più famosi della matematica. In essa si legge che è impossibile dividere un cubo in due cubi, o in generale qualsiasi potenza maggiore di 2 in due potenze di quello stesso grado. L'ipotesi, nota come l'ultimo teorema di Fermat, afferma quindi che non esistono soluzioni all'equazione x alla n più y alla n uguale z alla n se n è maggiore di 2. La dimostrazione del teorema resta un mistero per più di 3 secoli, impegnando molte delle menti più brillanti della matematica. È probabile che Fermat abbia ricavato una dimostrazione semplificata del teorema, valida per n uguale a 4. Nei secoli successivi si tenta dunque di giungere a una dimostrazione generale del teorema. Un importante contributo è in seguito fornito da Ernst Kummer, che arriva a dimostrare il teorema per tutti i numeri primi minori di 100, ad eccezione di 37, 59, 67. Sarà infine il legame con la geometria ad aprire la strada al passo successivo e alla dimostrazione conclusiva. Nel 1985 Gerhard Frey nota un legame tra il teorema di Fermat e un problema noto come congettura di Taniyama, riguardante le curve ellittiche. Un anno più tardi Ken Ribet dimostra l'esistenza di questo legame. Questa scoperta stimola Andrew Wiles a considerare da una nuova prospettiva il teorema che l'aveva affascinato fin da bambino. Finalmente, nel 1995, Wiles espone la dimostrazione dell'ultimo teorema di Fermat, diventando la celebrità matematica più famosa al mondo.
Fermat's last theorem, the problem that he wrote in his marginal notes, he claimed to have solved. In the following century, Euler set about trying to find a solution and, in fact, even tried to get someone to look for Fermat's manuscripts, see if they could find anything. But Euler managed only to do the case n equals 3, that is, to show that there are no solutions to x cubed plus y cubed equals z cubed in whole numbers. The case n equals 4 is actually in Fermat's writings. But the cases for n bigger than 4 were not solved until the 19th century. So after Euler in the 18th century, this problem really went into kind of relapse for many years, until in the early years of the 19th century, when Dirichlet and Legendre managed to do the case n equals 5. And then in the 1840s, Lamé, a physicist, claimed to have found a general solution. And there was great excitement at the Paris Academy, and other people thought they'd found a way of solving this problem. But in fact, there was a mistake in the proof. There was a fundamental gap in understanding. And this gap in understanding had already been resolved by the German mathematician Kummer a year or two previously, but no one in Paris was aware of what he had done. So the problem is the following. People tried to solve this equation by inventing a new number system. So the new number system involves not just using the ordinary integers, but some special complex numbers as well. Now, in this new arithmetic that was invented to try and solve this problem, you would try and solve the problem in the bigger arithmetic. And if there are no solutions in that bigger arithmetic, then of course there are no solutions in the original arithmetic either. But what they forgot was that in our arithmetic, in ordinary numbers, we all the time use one principle, which is the principle of unique factorization. That is, if you take any number like, say, 28, you can write it as 2 times 2 times 7. That is as a product of prime numbers. And you can do that in one way, and one way only. Similarly, you can write 15 as 3 times 5. You can't imagine writing it as a multiple of 2 different prime numbers. 15 is 3 times 5. There's no other way of writing it. But in these new number systems that they'd concocted, this principle no longer held. Now, they'd been assuming this did hold, and perhaps part of the reason is that no one had really worried about this issue previously very much. It was so taken for granted in the way one did arithmetic. But when one worked in this new, highly artificial number system involving complex numbers, one had to worry about it, and it didn't work. So this German mathematician Kummer had tried these new number systems and had shown that this particular problem fails, this unique factorization fails in general. But he managed to get round it, and he managed to solve Fermat's problem for all primes less than 100 except 37, 59, and 67. Kummer really initiated a whole new start to number theory, what is now called algebraic number theory. It became a way of trying to solve equations by inventing new number systems. And so for the next 100 years, people tried to develop new number systems to analyze how they worked, to see when unique factorization worked and when it didn't, to find something that would substitute for it. It was a very exciting period, this period in the middle of the 19th century. And of course, many people tried to solve Fermat's last theorem to get back to the original problem that had initiated Kummer's study in the first place. But by the middle of the 20th century, people had really despaired of this approach to the problem. Somehow, every time one felt one was getting a bit closer to the problem, some new obstacle would show up, and it was always related to this old problem of unique factorization. Curiously enough, Fermat, in his original work, had understood unique factorization in his own language. He had understood it in other problems that it didn't hold. So whatever he was doing for Fermat's theorem, it seems unlikely that he'd made that particular mistake. So it's still open what Fermat was trying to do, and perhaps someday someone will find some manuscript of his that might throw light on it. The tradition of number theory, of solving equations in integers, is really a very specialized and intricate mathematical development, which was slightly off the mainstream. In some sense, algebra itself is the study of solving equations, but not in integers. So throughout the period of the Renaissance in mathematics, the 14th, 15th, 16th centuries, when people are rediscovering and taking further the work of the Greeks, the Italian mathematicians, the Italian algebraists, have been trying to solve higher and higher order equations. So first, there's the great case of the cubic equation, which caused a lot of controversy. This was first solved by our modern understanding by Del Ferro. But in the way they wrote mathematics at the time, they thought there were perhaps 20 different kinds of cubic equations that had to be solved, and he'd only solved one of them. In our modern language, we can reduce them all very simply to the one Del Ferro solved. But at the time, they thought they were all different. So Del Ferro had solved one particular equation. Now, it was the tradition at the time to show your mathematical strength by challenging some other mathematician to a duel. This wasn't a duel fought with swords, this was a duel of mathematics. You would set some problems to your rival would set you the problems, and you would see who would do better. So around this time, after Del Ferro died, he passed on his solution to the equation, which he kept to himself, passed on to his student, and an upstart young mathematician by the name of Tartaglia challenged the student to a duel. So this was the way to achieve fame. If you won a mathematical duel against some prominent mathematician, then you would get fame, you get a position, you get support for doing your mathematics. So Tartaglia challenged this student of Del Ferro to a duel. Del Ferro set lots of problems in his style. Tartaglia set some other problems, solving cubic equations, but not the same kinds of cubic equations, to the student of Del Ferro. Just before the contest was actually take place, Tartaglia actually understood how to do the case that Del Ferro had done. So when the contest actually took place, Tartaglia could solve all the students' problems, and Tartaglia made sure he set ones that the student could not solve in his turn. So Tartaglia came out, great success, great fame, and became very prominent. Cardano, who was a very prominent mathematician at the time, heard about this and desperately wanted the answer out of Tartaglia. So he tried every trick he could think of to extract the answer from Tartaglia, but of course the secret is your livelihood. You don't want to give it away. So Tartaglia kept putting him off and trying to say, well, I'll tell you someday, But Cardano was not satisfied, and finally he lured him with a bait of some very lucrative position. And Cardano swore on an oath that he would never divulge this in his lifetime. If Tartaglia would just tell him, he would write it down in code so no one would be able to read it, even after his death, and so on. So Tartaglia finally agreed, and he wrote the solution in the form of a poem to Cardano. But even then, it seems he didn't want to give away the whole answer, because there are one or two tiny deviations from the correct formula in the poem, which perhaps he put in deliberately to distract Cardano. So when Cardano actually tried to apply it to solve the problem, it didn't actually work. So Cardano went at him again, and finally it seems he got the full answer out of Tartaglia. Well, Cardano kept his promise more or less for a while, until at some point he heard from Del Ferro's nephew what Del Ferro's original solution was. Del Ferro's nephew had found it in Del Ferro's notebooks, and so Cardano found the original solution from Del Ferro's nephew, and then felt he wasn't obliged by this oath anymore, and proceeded to publish the solution of the entire cubic equation. Tartaglia was furious and demanded another duel with Cardano this time. Cardano said he wouldn't, but one of his students, Ferrari, would do it. Tartaglia didn't want that at first because he really wanted revenge on Cardano, but finally accepted, and unfortunately for Tartaglia, he lost to this young Ferrari. So in this way, Ferrari then went on and solved the quartic equation. The quintic equation, that is an equation of degree 5, was still unsolved into the 19th century, and it was only when Abel appeared and proved that the general quintic equation cannot be solved using a formula that this problem was finally set to rest. Young French mathematician Galois then explained how you could look at an equation and decide whether it was solvable. That is, you can find some formula for the solution or when you can't. So this period of development of solving equations just algebraically spanned from the 13th, 14th century through to the middle of the 19th century. And at this point, number theory and algebra start to come together, because these techniques that have been used in algebra for solving equations actually start to get used in the number theory. So this is partly what Kummer was able to do, to employ these algebraic methods to actually study the number theory problems, that is, problems like Fermat's last theorem. After the period when people tried to solve Fermat's last theorem by using the methods of Kummer had died down in the middle of the 20th century, people had really, in some sense, lost hope in solving Fermat's last theorem. At the end of the 19th century, there was a prize set up by a German by the name of Wolfscale for the solution of the problem. And that had led to a number of interesting papers, interesting developments, but none of them looked as if they were getting close to solving the problem. The problem had been, in some sense, relegated to the list of problems that mathematics hadn't been able to solve and perhaps would just have to put to one side. Then a remarkable thing happened. A German mathematician by the name of Gerhard Frey found a remarkable link between this problem, the Fermat problem, and a problem that was known as the Taniyama-Wei conjecture, which was a very prominent, essential question really in a different field of mathematics. It was a problem that involved calculus rather than algebra, or at least that's what it seemed. This problem, the Taniyama-Wei conjecture, is a problem about a different kind of equation, but it's about trying to associate an object from calculus to that different kind of equation. So the link was totally unexpected, this link that Frey found between these two subjects. And in a way it related the number theory of arithmetic with the number theory of calculus. Well, some people took this as a sign of how hard Fermat's last theorem was. But some people might take this as a sign that actually Fermat's last theorem, it's a new lease of life for it, because finally it's going to be a consequence of a problem that mathematics can't put to one side. I mean, there are some problems that just stand in the way. You have to solve them before you can really move on in mathematics, whereas Fermat's last theorem could always be put to one side. Well, Frey's idea was only an idea, needed some substance to it, and that was provided quite soon afterwards by American mathematician Ken Ribet, who actually showed that this other problem, the Taniyama-Wei conjecture, if solved, would imply Fermat's last theorem. So I got very excited at this point. I came to number theory actually as a child because I'd been excited by Fermat's last theorem. I got a book out of the public library and it described this problem on the cover and explained about the prize and explained the history, and I was hooked during my childhood thinking, well, maybe Fermat did have a solution and Fermat didn't know too much more than I did in terms of sophistication in mathematics. Of course, he was a great genius of the 17th century, but that mathematics was pretty old by the time I was a student. So I thought, well, I'll just try it, bare hands methods. Maybe I'll be lucky and I'll find the solution Fermat had. Of course, if Fermat hadn't had a solution, then I wasn't going to have a chance. So I pored over Fermat's works and tried to understand how he had thought, and I tried to think in his way, and I tried to solve the problem that way. But when I became a professional mathematician, I realized that that was really hopeless, and I wouldn't even get any side benefits out of this. Nothing would come of it. There were other mathematicians who'd spent years and years of their lives trying these old-fashioned methods without actually getting anything out of it. So when I heard about this result of Ribbit, linking it to the Taniyama-Weyl conjecture, I was really thrilled, because this was the part of mathematics that I knew a lot about. I hadn't actually tried to solve the Taniyama-Weyl conjecture. I thought it was too hard. But I certainly believed it was true, and I certainly believed that it would one day be proved. And at that point, I just decided I have to work on this, and I did. I realized quite quickly that I wasn't such a good idea to tell everybody what you're working on when it would involve solving Fermat's last theorem, so I kept it to myself for a while. And I just worked on it over the years and made steady progress until 1991, when I really made a crucial breakthrough, and I reduced it to a kind of formula that was also conjectured and which seemed just at the edge of what was provable. That is, simpler cases of this formula had been proved, harder cases had not. This was just at the boundary. So I tried all the available techniques, and I thought I'd solved it in 1993, and I announced the proof. And as is now known, there was a mistake in that. But after a year, this got resolved and finally was able to solve the problem. So the problem got solved by introducing a completely different line of thought. Frey had brought together two strands of mathematics that had seemed totally unrelated. And in some ways, this is what makes number theory so captivating for the practitioners. You have a simple problem in terms of solving an equation in integers, and yet to solve it, you use the most sophisticated and ingenious techniques from all areas of mathematics, from calculus, from differential equations, from logic, from algebra, from all areas of mathematics. And that's the real thrill of number theory. It's very interesting in number theory. Many mathematicians start in other subjects, and then they try number theory, and they never leave it. People move to number theory, but it's like a black hole. You can't escape. Once you've caught the passion and the attraction of it, you can't get away from it.
Sul finire dell'Ottocento viene istituito, per volontà del chimico Alfred Nobel, l'omonimo premio, che ancora oggi rappresenta il più alto riconoscimento assegnato in campo scientifico e letterario. Tra le varie discipline considerate per questo premio spicca l'assenza di una scienza che ha senza dubbio un'importanza fondamentale: la matematica. A questa mancanza si è ovviato premiando illustri matematici come John Nash o Robert Aumann con il Nobel per l'economia. Esiste tuttavia un premio di grande prestigio, considerato il Premio Nobel per la matematica. Si tratta della medaglia Fields, assegnata ogni 4 anni a giovani matematici particolarmente brillanti, di età non superiore a 40 anni. È questa rigida regola che ha causato l'esclusione di Andrew Wiles dal premio, avendo dimostrato il famoso teorema di Fermat a 42 anni. Dalla seconda metà del Novecento i premi assegnati in campo matematico aumentano. Nel 1978 viene istituito il premio Wolf, senza imporre un limite d'età. Similmente viene assegnato ogni 2 anni il premio Schock per la matematica dall'Accademia Reale Svedese delle Scienze. Con il grande sviluppo dell'informatica, a partire dagli anni '80, l'Unione Internazionale dei Matematici istituisce nuovi premi. Il premio Nevan Linna per gli aspetti matematici della scienza dell'informazione e il premio Gauss per la matematica applicata alla tecnologia.
In some sense, modern mathematics really came together with Gauss. And while number theory had been this wonderful, specialized area that Fermat had studied, and then Euler and Legendre, Gauss, as a teenager, wrote the founding book in the subject. Fermat had published basically nothing. There was some correspondence and there were notes in the margins of his copy of Diophantus, but he hadn't published. Euler, of course, has published so much that we still don't have a complete edition of his works even now. But number theory was just some tiny part of that. But Gauss wrote a book that was actually about number theory, Disquisitiones Arithmeticae. And he wrote this basically as a teenager. It appeared when I think he was 21, right at the end of the 18th century. It finished the work in, I believe, 1798. And in this, he laid down a kind of framework for future work in the field. He laid down that you should study equations, but you study equations first in what's called modular arithmetic. That is, you solve equations modulo a prime number. In his book, you can find the roots of problems that were only solved 150 years later. The important work of Weil and Deligne in the 20th century really has its roots in the work of Gauss. So Gauss set a framework, and then the young mathematicians at the time worked from that. So the two great directions that number theory took, perhaps the kind of calculus direction taken by Dirichlet and the algebraic direction taken by Kummer and then Dedekind, had their roots in this work of Gauss. One of the most beautiful theorems in this period was one by Dirichlet, which says that if you look in an arithmetic progression, that is, you look at all numbers which are, for example, 2 bigger than a multiple of 5, then you can always find infinitely many primes in this progression. So this sounds like a very arithmetic statement. That is, there are always primes, like 7 is a multiple of 5 plus 2. 17 is 3 times 5 plus 2. And both 7 and 17 are primes. And what it's saying is you can infinitely often find primes of this form. What's fascinating about Dirichlet's solution to this problem is that he used calculus to solve this. And as far as I know, to date, there's not even now an algebraic solution of this problem. And that's one of the fascinations of number theory, is that you really need calculus to solve many of these algebraic or arithmetic problems. And sooner or later, any of these great problems requires some injection of mathematics from seemingly a totally different area. from calculus. Gauss's influence was phenomenal. He laid the foundations for all the basic principles that were used in the development of number theory. Fermat's last theorem wasn't the only mathematical problem that came out of Fermat's marginal notes or from his correspondence. One of the most fascinating was this problem about squares and cubes. So, which numbers can be written as the difference between a square and a cube? For example, can 2 be written as the difference between a square and a cube? And the answer is yes. It's 27 minus 25, and 27 is a cube. It's 3 times 3 times 3, and 25 is a square. It's 5 times 5. Fermat was interested whether that was the only solution, whether that was the only solution in integers, whether that was the only solution in rational numbers. He was interested, if you find one solution, can you find more? And he developed a whole theory for trying to solve this question. But in fact, this question is still unsolved today. There is no known algorithm such that if you give me a number like 53, can you write 53 as the difference between a cube and a square? So there's an algorithm for determining whether you can find it as the difference between a cube of an integer and the square of an integer, but not whether you can find it's the difference between a cube of a rational number and a square of a rational number. Around 1960, two British mathematicians by the name of Birch and Swinnerton Dyer came up with the magnificent prediction for equations of this kind. And in this prediction, they say how you should be able to determine whether there are solutions. And if so, in some sense, how many, and even more daringly, maybe find them. This problem's been open for 50 years now, and it's still far from being solved. But it's a fascinating problem. Its answer lies in associating some calculus object to this equation. In fact, it's the same calculus object which is given by the conjecture of Taniyama-Wei, the conjecture that was so crucial in solving Fermat's last theorem. So the hope is that this piece of calculus that gets associated to the equation will one day give us the way to solve that problem. It may sound like a very artificial problem, but in fact it's not artificial. It's a typical case of maybe the general problem. So the general problem might be, can you solve an equation in 2 variables? Any equation. So you have x to the 5th plus 5, x cubed y to the 11th equals 7x squared plus 3y plus 2. That's an equation. Can you solve that equation? Well, we know how to classify these equations, and in perhaps one of the most exciting mathematical events I remember in my lifetime, most of these equations were solved in the sense that we found that there are only finitely many solutions for most of these equations. And this was solved in 1983 by Gerd Fultings, and this had been known as the Mordell conjecture. It had been open a long, long time. The problem about the difference between a cube and a square is not one of these equations. It's a special case which can sometimes have infinitely many solutions and sometimes have no solutions. And we don't know how to distinguish when it does and when it doesn't. So this is prototypical of the case which Fultings' theorem did not include. So we've come a long way since the 19th century. We can solve many, many equations in two variables, but not all of them. And this one, which is also one of the Clay Foundation prize problems, is, I think, the most beautiful and exciting of the problems in arithmetic left over.
La storia della matematica è costellata da ardui problemi che hanno impegnato nel corso dei secoli le menti degli studiosi. Alcuni hanno avuto facile risoluzione, per altri sono serviti anni di tentativi, di parziali successi e di grandi sconfitte. I matematici hanno spesso fatto previsioni sui tempi necessari a sciogliere questi enigmi, assumendo sempre che per ogni quesito esista una soluzione razionale che, se oggi non è nota, un giorno lo sarà. La teoria dei numeri, in particolare, è ricca di problemi all'apparenza semplici e tuttavia ancora oggetto di studio. Un esempio è quello dei numeri perfetti, uguali alla somma dei loro divisori. Euclide, in seguito Eulero, sono riusciti a caratterizzare i numeri perfetti pari, ma ancora oggi non si è dimostrata la loro infinità e non si è a conoscenza di numeri perfetti dispari. L'infinità dei numeri primi è invece nota già dall'antichità. Tuttavia, numerose ipotesi che li riguardano non hanno ancora una dimostrazione, come la congettura di Goldbach, per cui ogni numero pari maggiore di 2 è la somma di due numeri primi. O la congettura dei numeri primi gemelli, che asserisce l'esistenza di infiniti numeri primi, la cui differenza è uguale a 2. Il più importante problema aperto della matematica è l'ipotesi di Riemann, che afferma che i numeri primi si distribuiscono all'interno della sequenza dei numeri naturali seguendo una particolare funzione, chiamata funzione z di Riemann. Il Clay Mathematics Institute ha stanziato premi milionari per chi riuscirà a risolvere questo e altri problemi del millennio ancora insoluti, che lanciano una sfida secolare e affascinante ai futuri matematici.
It's very interesting that originally when the Greeks and the Babylonians were doing arithmetic, it was really tied with geometry. Everything was related to geometric objects. The sums of squares equaling another square, of course this was Pythagoras' theorem, but even it seems the concept of the Greeks was geometric. That is, they could understand multiplying three numbers together because that would give you a volume. But why would you multiply four numbers together or even more? So that part of the development of algebra was to remove the geometry. That is, the algebra freed of geometry enabled one to perform operations that one couldn't really imagine. Just as when one introduced complex numbers, it freed one to solve equations in a way that didn't really seem to make sense to the people who solved them. But interestingly, after a long period where these subjects develop independently, we get back to a stage where actually the geometry is very helpful for solving these problems. We don't want to live apart the algebra and the geometry forever. And a lot of what I do actually involves bringing geometric techniques back into number theory. So I've talked about equations possibly having infinitely many solutions. This problem, for example, that Fermat studied, the difference between a cube and a square being a given number. Or as I might put it in algebraic notation, y squared is some given number plus x cubed. Well, the way Fermat thought about this was he would actually draw a picture of this equation, and he would draw supposing he had a solution, he would draw a tangent at that point. And the tangent at that point would hit the curve again at another point. He'd take that other point and draw the tangent again. That would hit the curve at yet another point. At that subsequent point, he would take the tangent again and it would hit the curve again. Now, if you keep repeating this process, one of two things can happen. You can get into a loop and it can go back to the point you started with and you just keep going round and round and round. And you only get finitely many points. Or you can keep going on forever. So this is what we don't know how to determine, is whether it goes on forever or whether it comes back. And if it goes on forever, of course, we have infinitely many solutions to our original equation. And all these solutions will be rational numbers. You start with rational solution. This chord and tangent process, as it's called, will give you infinitely more rational solutions. If you get back to where you started with, then you've got finitely many solutions. But whatever the solution is, it is somehow geometric. And much of the success of modern number theory involves understanding the geometry, how these solutions evolve geometrically in time. So I've spent a lot of time trying to solve this particular problem by using geometric methods, as well as methods from calculus. In fact, what seems like the biggest stumbling block in this particular problem is to try and find some geometric way of writing down a solution in the first place. So again, using this Taniyama-Wei conjecture, which I said was from calculus, but actually has an interpretation in geometric terms as well, you can sometimes give a geometric construction of a solution. It's a very beautiful solution, but unfortunately, it only works sometimes. We know exactly when it works and when it doesn't. But when it doesn't, we have no idea how to make any solutions at all. It's a baffling problem. I think this is one of the great appeals of number theory. These problems last for generations and generations. We inherit them, yes, from the beginning of the 20th century or even the middle of the 20th century, but we even inherit some of them from 1,000 years earlier. In some sense, these problems of cubic equations I've been talking about go back 1,000 years. Of course, some of the problems from ancient times we discard, more or less because we feel they're not quite structurally part of mainstream mathematics. So a perfect example of this is perfect numbers. There's always been a question, are there any odd perfect numbers? And no one knows the answer to that. A perfect number is a number which is the sum of its own divisors. For example, 6 is 1 plus 2 plus 3. That's a perfect number. Are there any odd ones? We don't know. The even ones, in some sense, can be classified, though again, it's hard to actually predict exactly where they are, but we know a kind of formula for them, and we can certainly generate many, many of them. But odd ones, we have no idea. On the other hand, we don't really believe it's a very good problem anymore. So some of the problems get left aside, but on the whole, the great appeal of number theory is this kind of permanence. You feel you're part of a field of inquiry that has been going on since antiquity. And you feel that it's something also that if you were to go to some other corner of the universe, the same problems would be there. It's not something that's special to our civilization. It's not like a work of art or a piece of music. It's not something that another culture would just find very strange. Another culture might simply not understand that music is actually a satisfying experience to us. They may of course not even have hearing at all. One just feels that mathematics, and number theory in some sense is the most pure form of it, is something that would be common to any corner of the solar system, of the universe, of other universes. It's part of reason itself. And it has an intrinsic beauty for that, which is not like the beauty, the transient beauty of works of art, which is all the more precious for its transience. It's a kind of permanent, almost cold beauty that is there forever and is part of the very fabric of reason and nature itself.